This is for Chem 1211. This is going to be sections 3.8 to 3.9. Today we're going to be talking about electron configuration. So we talked about our orbitals. We've got s, p, d orbitals. We've got energy levels, and we got to think about how electrons are going to be put into those different orbitals. Now, electrons will fill lowest energy level first. And so thinking about this image, if energy increases to the right, we're going to be filling the 1s first, then we'll fill the 2s, then we'll put electrons in the 2p, and there's 3 of those shapes there. Then the 3s, and then 3p, there's 3 shapes there. Then we actually do something weird. We don't go to 3d, we go to 4s, and then there's 5 shapes in the 3d, and you can see here we have 7 shapes in the 4f. Each shape can hold 2 electrons. So if I have 2 electrons, they'll be in the 1s, and the next 2 electrons will be in the 2s, and then the next 6 electrons will be in the 2p, and then the next 2 will be in the 2s, and then so p can have 6. So s can have a max of 2 electrons. P can hold a max because it has 3 shapes of 6 electrons. D, it has 5 shapes, can hold a max of 10 electrons, and F has 7 shapes, it can hold a max of 14 electrons. I didn't show you the 7 F shapes because they're really complicated, but you can Google them if you're curious. Now, you may think, oh, I have to memorize this order. You don't. The periodic table can be put together in a way that helps us with this. So imagine that here we have the S block on the periodic table, which would include everything in the top first 2 columns, but add in helium. So we call that the S block. Then the P block, we would call this area in blue. The D block would be the area in orange. And then the F block would be the area down here in purple. We can think of the squares as the number of electrons we can put. So I just told you 2 electrons max in 2s. Well, there's 2 squares thick for the 2s. That's 2 electrons. And so you can just divide that number in half to know how many shapes. If you can fit 2 electrons, there must be 1 shape. So there's 1 shape for the 1s, 1 shape for the 2s, 1 shape for the 3s. For P, we can hold 1, 2, 3, 4, 5, 6 electrons. So there's 6 squares, so 6 electrons can be held, which means that we can have 1, 2, 3 shapes because each shape holds 2 electrons. For D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 holds 10 electrons. Therefore, we can have 1, 2, 3, 4, 5 shapes because there's 2 electrons per shape. And then, of course, F is 14 across, and so you can have 7 different shapes. So you don't have to memorize the shapes and how many electrons we can hold in each orbital. You could just use the periodic table. Now, another thing we like to do is just go across the periodic table, starting with atomic number 1, and then go through it. So atomic number 1 and 2 are in the 1s. Then we go to 2s. That's atomic number 3 and 4. Then we go to 2p. That's atomic number 5 through 10. Then we go to number 11, that's 3s. And then we go to number 12 is 3s, and then 13, that's 3p. And so you can see we're getting our order from just following the atomic number and where we are. The energy level corresponds to the period for the S and the P blocks. So energy level equals period, and the period is the row for S and P. And then for D, energy level equals the period minus 1. And then for F, it's minus 2. So we can get everything we need to know about where our electrons are and what our electron configurations are from the periodic table. So even though the D starts on 4, it's going to be labeled as 3D, but we still go in the same order. So we go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. Now the F starts here, so we would do 1 and 5d, and then we would do 4f, because it's in level 6, but we go back 2. So 4f, and then we come back to finish the 5d, and then 6p, and then we keep going. So you don't have to memorize, you only have to know this information, and then where the S, P, D, and F blocks are. This is going to make more sense once you start actually practicing it, and it is a lot easier than it seems if you just give it a chance and you just try to do some practice. Use your periodic table. So make sure you're bringing your periodic tables to class and that you have the periodic table that you're going to have on your exams, which I hand out to you in class and is posted in D2L. So you're familiar with that particular periodic table because sometimes where they put the F block start is a little different. So what is an electron configuration? These are all kind of messed up. So let's rewrite these. So electron configuration, let's look at lithium. So lithium is number 3. So we have 3 atomic number of 3, so 3 protons, and then 3 electrons if we're neutral. So we're going to assume we're doing electron configurations for now, that we're talking about neutral atoms. So I say, what's the electron configuration for lithium? We assume neutral lithium. So we need to fill to number 3. So we start at number 1, that's hydrogen. So hydrogen is an energy level 1, it's in the S block. And then we need to go through 2 squares or 2 electrons in the 1s to get through the 1s. We're trying to go out of it. So we'll say 1s2. The numbers at the top tell us the number of electrons, which is the same as the number of boxes. This tells us the block or the orbital type. And this tells us the energy level, which can be the same as the period, but it can also be a little different if you're D or F. So that 1s2, if we stop at 1s2, we would have helium's configuration, but that's number 2. We want to go to number 3. So number 3 is going to be energy level 2, S block, first box. So we'll say 2s1. Then we have something called core electrons versus valence electrons. Core electrons are on the inside. Valence electrons are on the outside. The outside is indicated by the highest energy level. So the highest energy level here is 2. So we have 1 valence electron hanging out in the second energy level. And everything else is core. So the core here would be 1s2. If we, for some reason, wanted, this is already pretty short, but later we're going to want to condense it because we're going to follow this pattern. We could follow it all the way down to OG. We're going to use shortcuts. The shortcuts are going to be the noble gases, which remember are the far right column, group 18. These are noble gases because they have what everybody wants, which is 8 electrons on the outside. We'll talk a little bit more about those valence electrons, but just know that when you get to this point, it's kind of like a checkpoint in a video game where if you go past, let's say we're going all the way down to somewhere down here, we've done all this work, we get to here. If we instead don't want to go all the way from number 1 again, we could just say, all right, remember the last time we were at a noble gas, and then we'll put that noble gas in brackets, and then we'll start there and we'll finish the work. So if we look at lithium, the last noble gas that comes before lithium is helium. So we'll put helium in brackets, and then we'll start from there. So helium is number 2. So we look at number 3, that's 2s1. So you notice that it'll help us identify not all the valence, but what's on the outside in general for the most part. So why don't you try nitrogen? So try nitrogen. So pause and try that one. So for nitrogen, and again, they kind of got this all messed up. The electron configuration should be 1s2, 2s2, 2p3. Or we can do helium, 2s2, 2p3. And that's because nitrogen is here. And so we have to go 1s2, 2s2, 2p1, 2, 3. The noble gas that comes before nitrogen is helium. We can't use neon because neon comes after nitrogen. So we got to use the one that comes before. Now, we sometimes need to know exactly what's going on inside of that. Like, what do those electrons look like? So we use these arrows to give us an electron. And if you have an up and down, that's an electron pair, a pair of electrons. So how do we do this? So I'm going to go back, take you back in time, and we're going to fill this up. So you're going to take your electron configuration, and we're going to look at how many actual shapes do we have in each orbital. We know S has 1 shape, so S gets 1 box. So for orbital diagrams, S gets 1 box. P has 3 shapes, so we're going to have 3, and it's equal in energy. So a long box with 2 dividers to give us 3 different boxes. D has 5 boxes, so a long box with 4 dividers. And then F would have 7 boxes, so a long box with 6 dividers. Don't do individual boxes and don't do lines. If you want to do lines, you can, but you got to make sure that if you do lines that you label them like this, where you can kind of wrap it together or use some sort of brackets. I prefer the boxes. I think they're easier to read for an instructor's point of view, and they're easier for you to look at in your notes. So draw your boxes first, always. So first, look at your electron configuration. We know we need a 1s, a 2s, and a 2p. Ignoring the number of electrons, draw your boxes. Now place your electrons in. As we place the electrons in, we're going to pretend like we're going to start with the lowest energy first, fill it up. So lowest energy is 1s. You can put 2 electrons in each box, remember? So 2 electrons in each shape. So 1 up and 1 down. We got to put 1 up and 1 down because no 2 electrons can be exactly the same. So if I'm a 1s electron, you can also be a 1s electron. You can be my partner, but you gotta go down. So we'll talk more about what those ups and downs mean in the next class. So next up we have 2s. So we'll put 2 in the 2s, 1, 2. And then we have 2p. Now each of these boxes is actually the same energy. So if each of these boxes is the same energy, we're not going to put electrons in like this because if we do this, then the electrons are repelling each other. They're both negative, so they don't actually really want to be together. If they can help it, they'd rather be in their own box. So this is not going to be correct. So what is going to be correct is up here. So you're going to put 1 electron in each box. Then if you have to put in more, you will fill them up. So that's why I always say draw boxes first, because otherwise you may wind up drawing something with only 2 boxes for 2p and then filling them up that way for 2p3. This is going to come with practice, y'all, so don't, it seems like a lot and weird right now. It's not intuitive. Just give it some practice. Start with electron configuration and then build up to the orbital diagrams. So here's the orbital diagrams and electron configurations for the first 10 elements, and you can literally see how we fill up those boxes there. For condensed electron configuration, here's a quick note. You actually cannot do this. Cannot use noble gas for that noble gas. So what it means is if you're drawing electron configuration for neon, you can't just put neon in brackets. Because imagine you're trying to tell me what the electron configuration for neon is. You can't just say the electron configuration for neon is neon. If I don't know what neon is, you got to tell me, okay, remember, go back to helium, and then I'll tell you from there. I'll explain another way to look at this in class, but just keep that in mind. When you're doing it, if you're doing noble gas, configuration for a noble gas, you cannot just put that noble gas in brackets and call it a day. You got to go back to the previous noble gas and then work forward. So here are some alkali metals. Notice that the alkali metals all have this 1 electron hanging out on the outside. They all have 1 valence electron. They all have 1 valence electron. As a matter of fact, all alkaline earth metals also have the same number of valence electrons. So let's go to a periodic table. Don't know that I have one in this slide set. If we go to a periodic table, and you can draw this on your periodic table, maybe you want to grab one that you can book notes on, and then have another one that you print out or grab from class that you can have blank to study with. But basically, your valence electrons across the periodic table, and I'm going to have to change this. I can already tell myself I'm going to have to change this. Need more space. So, valence electrons across the periodic table are going to be 1 for this column, 2 for this column, skip the valley, 3, 4, 5, 6, 7, and then 8, except for helium, because helium can only have 2. So these are going to be our valence electrons. And for each family, or each group on the periodic table, they all have the same valence electrons down. So 6 for all of these, 8 for all of these, 7 for all of these. The only exception is 2 for hydrogen or helium up here because it's so small. So all alkali metals specifically. All alkaline earth metals have 2. All halogens have 7. We skip the valley and we skip the F block down there. The periodic table can be really helpful because now you don't have to look at electron configurations to tell the valence electrons, which is important because they're the outer electrons that do the interacting with other atoms. And so we'll use those for bonding. And these are, yes, it's easy to do abbreviated, but if you just look at the periodic table, you can tell valence really quickly. When we're dealing with ions, so let's say that we have a positive ion, which means we lost an electron. So if we lose an electron, we have to show that in configuration that we would lose an electron. So if sodium is neon 3s1, if it loses an electron, it looks just like neon. If chlorine gains an electron and it's helium 2s2 2p5, it looks like 2s2 2p6, which is neon. We say that they're isoelectronic since they have the same electron configuration. We can also think about this as same number of electrons. They both look like neon. So they are isoelectronic. It's not isoelectronic if it's the same number of valence electrons. I'm talking about total electrons, not valence. So think about if I have to remove electrons, if I have to add electrons. One note about removing electrons when you're dealing with transition metals. So we always remove the s electrons before we move the d electrons. So remove 4s before 3d. Why? Because 4s is on the outside because it's a higher energy level. 3s is higher, 3d is higher energy than 4s, but 4s is on the outside. So we're always going to remove from the outside before 5s gets removed before 4d, etc. So if I need to remove electrons from something that has a d configuration, we need to make sure we remove from the outside first. And I wouldn't write the electron configuration like this. I would write it as 4s2 3d8. I always write it in the order in which I find it on the periodic table. So if that makes sense, if not, text me and I can help you out. So let's try this. Write the condensed or abbreviated electron configuration for each of these ions and then which ions are isoelectronic with neon. So pause it and try this one. So hopefully you paused and were able to work on this. So here are your electron configurations for the normal elements. And then if we were to take consideration of the charges, here's our new number of electrons. So if we look at the number of electrons normally for oxygen, it's 8, but now it's 10. This was neon. This one is neon. 18 is argon and argon. So oxygen with a 2 minus is isoelectronic with magnesium with a 2 plus. Both look like neon. Chlorine with a 1 minus and calcium with a 2 plus both look like argon, which is number 18. So we can quickly just look at number of electrons, or you can look at electron configurations. So here are your electron configurations. I don't like that they did this. It should be like this. But you can see that the top two have the same and the bottom two have the same, which means their top two are isoelectronic with neon and bottom two are isoelectronic with argon. All right, we will do more practice with this in class.